Today, we're going to get into the states of matter. The absolute foundation of our physical world. We're going to explore the three we see every single day, and then a fourth one that basically powers the entire universe. So let's dive right in. So let's start with a question. Think about a rock, a glass of water, and the air you're literally breathing right now. I mean, they seem totally different, right? But what's the one fundamental thing they all share? Well, the answer is they're all made of matter. And matter is really just the stuff of the universe, anything that has mass and takes up space. All of this stuff is made of these unimaginably tiny particles called atoms.
So, here's our game plan. We've got a handle on what matter is. Next, we'll break down solids, liquids, and gases. Then, we'll look at how they actually change from one to another. And finally, we'll get into the really cool stuff, the fourth state of matter, plasma.
All right, let's get into the main event, the big three states of matter that we all deal with every single day.
This table gives us a great bird's eye view. You can see solids are rigid. They hold their own shape and volume. Liquids, well, they flow and take the shape of whatever container they're in, but their volume stays the same. And gases, they're the free spirits. They just expand to fill whatever space you give them, completely. So, what makes a solid so solid? It's all about how its particles are arranged. In a solid, they're packed together in this tight, orderly structure. They're vibrating, sure, but they're basically locked in place. That's why a rock is, a rock. Now, with liquids, things get a little looser. The particles are still pretty close, but they aren't stuck. They've got enough energy to wiggle and slide past each other. It's exactly why you can pour water from a tall, skinny glass into a short, wide bowl. The amount of water doesn't change, but its shape does. And then you have gases. Here, the particles are just going wild. They're flying all over the place with tons of energy, and they're super far apart from each other. All that empty space between them is the reason a gas has no definite shape or volume. It's also why you can compress a gas so easily. Okay, let's talk about density, which is really just how much stuff is crammed into a certain amount of space. For most things, like this iron here, the solid state is way denser than the liquid state. It just makes sense, right? The particles are packed in tighter. But, and this is a huge but, water is the big exception. It's just wonderfully weird. When water freezes, its molecules actually form this crystal structure that takes up more space. This makes solid ice less dense than liquid water, which is the whole reason ice floats. And it's not just a cool party trick, it's why lakes freeze from the top down, which insulates the water underneath and lets fish and everything else survive the winter. Pretty amazing. And just look at this chart. It really shows you the dramatic differences we're talking about. Solid iron is almost 8,000 kilograms per cubic meter. Water is at 1,000. And air? Whoa, it's that tiny little sliver down there at just 1.2. The difference is absolutely massive. It just drives home how spread out those gas particles really are. So we've got our three states, but they aren't set in stone. They can transform. So what happens when you add or take away energy? Let's get into how matter actually changes from one state to another. Okay, so when you add energy, usually in the form of heat, you get these kinds of changes. We all know melting, right? Solid to liquid. And vaporization is liquid to gas. But then there's this really cool one called sublimation, where a solid just skips the liquid phase entirely and goes straight to a gas. The perfect example is dry ice. It never makes a puddle. It just turns into this spooky cloud of carbon dioxide gas. And no surprise, it works in reverse too. When you remove heat, the particles slow down and they start to get cozy again. Condensation is when a gas turns back into a liquid. Think of the water droplets on the outside of a cold glass. Freezing is liquid to solid. And deposition is a gas going straight to a solid. That's actually how frost forms on a cold morning. We've nailed solids, liquids, and gases. But you know what? The story doesn't end there. It is time to go beyond the familiar and explore the fourth state of matter. So while we live in a world that seems to be all about those three states, they don't even come close to making up the whole universe. So what else is out there? Well, the answer is plasma. So meet plasma. Here's how it works. If you take a gas and you just heat it up to insane temperatures, the energy becomes so intense that it literally starts ripping electrons right off the atoms. What you're left with is this superheated soup of positively charged ions and all these free-floating electrons. It's basically an electrically charged gas.
And plasma is incredible because it's full of all these charged particles. It can conduct electricity. Now, here's the crazy part. While it's pretty rare here on Earth, it is by far the most common state of matter in the entire universe. Why? Because the universe is filled with places with extreme heat and energy, like our sun and every other star out there. Even lightning bolts, that's all plasma.
A neon sign is a perfect, everyday example you can see. You're just passing an electric current through a tube full of gas. That energy ionizes the gas, turning it into plasma. But when those electrons that got knocked off fall back and recombine with their atoms, they have to release that extra energy. And they do it in the form of bright, colorful light.
So if you take away one single thing about plasma, make it this. The absolute fundamental difference between a regular gas and a plasma is electricity. A neutral gas won't conduct it. A charged up plasma absolutely will. And that brings us to one last really fascinating thought. If plasma makes up something like 99% of all the visible stuff in the universe, powering the sun and all the stars, why is it so rare in our daily lives? It's a question that really makes you think about just how special and maybe how calm our little corner of the cosmos really is. Thanks for watching.